Yeah, thank you very much. I'm really happy to be here and see so many familiar faces. So today I'm presenting joint work in progress with Andrés Jaramillo Puentes on counting curves over an arbitrary field using tropical geometry. So actually I was here in March and I was also presenting this, so I decided to do it a little different this time. So let's see how this goes. I feel like there's not too many people here who actually know tropical geometry, so let me start with this. And for this, I can really recommend, there's a nice introduction by Erwan Brugale and Chris Shaw. And in the beginning, they have a slogan for what they do for tropical geometry, which is, let's study simple objects to provide theorems about complicated objects. So in the case today, the simple objects are tropical curves, which I will introduce first, and the complicated objects are algebraic curves. More precisely, I want to count algebraic curves by counting tropical curves. So this is the beginning of this really nice introduction to tropical geometry. And now I'm also following this introduction to introduce tropical curves. So. Okay. All right, so what is this? First, let me introduce the tropical operations. So let A and B be real numbers. Then the tropical addition, which I just do like this, I write addition in quotes, is supposed to be the maximum of A and B. And the tropical multiplication is the classical addition. Okay. This is not a field because I don't have inverses to the addition, but I have a neutral element if I add minus infinity, and this is the tropical semifield, T for tropical. So these are my operations, and now how do we want to, what should a tropical curve be? Well, let's think back to algebraic curves. One naive way to define them is as the zero locus of a polynomial in two variables, and that's exactly what we do here. So let's start with tropical polynomials. Let's do this in two variables. So this should look like something like this. I have some finite sum of aij, where the aij are real numbers, x to the I, y to the j, but everything in quotes. So that should be a tropical polynomial. Let's translate this. This is the maximum of all of these summands. And now we turn multiplication into addition. So we have aij plus I times x plus j times y. So this is a piecewise linear function. even convex piecewise linear function. So you just look at where this becomes max. And let's define a tropical curve to be the non-differentiable locus of this. And then I'll do an example and then mix it. So, does this fit here? Hopefully. So what should be tropical curve? Is the following. It's the non-differential locus of a tropical polynomial. Okay. Now there is no space. Let's call the polynomial pxy. So actually, let's call it gamma because it will be a graph. So we write this for the tropical vanishing locus of the polynomial. So this is the definition. So what does it mean that the polynomial is non-differentiable? That's exactly where this maximum is attained at least twice. So these are all points in R2 where the maximum, this maximum up there, is attained at least twice. So this is a graph. And we want to add some weights to the graph. Okay, now the definition of the weights is a little complicated, so I'll write it down and then I'll do an example. So for an edge E of this graph, I define the weight, so this is the weight of it, to be the maximum of the following. First over ME, and ME is all pairs ij KL, such that for all P and Q, for all points on the edge, this polynomial of P, Q is equal to Aij plus IP plus JQ, but also AKL plus KP plus LQ. So what does this mean? So I say I take the locus where the maximum is attained at least twice, but it could also be more than twice. So we have these linear functions up there. So there's at least two of these tuples where the maximum is attained, but there could also be more choices for this. So, but here, so yeah, there's at least two where the maximum is attained. Okay. All right. And then, maybe I should have not given the precise definition, but okay. So now we take the greatest common divisor of the absolute value of I minus k. So that's the first one, and then j minus l. So let's do an example. Let's do two examples. So first of all, what should the tropical line be? tropical line should be the vanishing locus of a tropical polynomial of degree 1. So let's take one. Pick one. So here I just took the following. I take a half plus 2x plus minus 5 times y. Let's translate this. This is the maximum of a half, 2 plus x, and minus 5 plus y. And now we are looking for the points where the maximum is attained twice. So I just equate 2 out of these. So when it's a half equal to 2 plus x, that's when x is equal to minus 3 over 2. When it's a half equal to minus 5 plus y, that's when y is equal to 11 over 2. So let this be the point minus 3 over 2, 11 over 2. And then let's equate these two, and this gives us that y is equal to 7 plus x, and this better be this line. So this is how a tropical line looks like. So what are the weights in here? So I started with this one here, where I equated this, and now I look at the i's and the j's, how many i's and j's there are, or what the exponents of my x's and y's are. So here the exponent is just x to the 0, y to the 0. Here it's x to the 1, y to the 1. So the absolute values is it's 1 and 0, and the greatest common divisor is 1. So the weight here is 1. Say the weight here is 1. Here the weight is 1. Here the weight is 1. And one usually doesn't write weight 1. Let's do another example where we have more complicated weights. So here we have something of degree 2. And let me just draw how this looks like. This will look like this. And here we will have weight 2, and here we will have weight 2. Why is this? Down here in this quadrant, 0 will be maximal, while up here, y squared, or 2y, will be maximal. So the difference in the exponents in the first coordinate is 0, right here, and then the second is 2. So it should be 2. Here this one will be maximal, so again we get a 2. But I'll give you a different definition of the weights. But I just wanted to say later. But I just wanted to say these are weighted graphs, and I wanted to find a simple example. So this is like the simplest I could come up with. Right. So these are tropical curves. Are there any questions until here? Okay. So I claim that these are our simple objects, but I need to introduce a little more about them. So now I want to introduce the dual subdivision, which is defined by a tropical curve. So let D be the degree of the tropical polynomial we started with. So this one is the tropical polynomial. And let's also call this the degree of the tropical curve. Then let delta D be the convex hull of the following points. I take 0, 0, I take d0, I take 0d. In R2. So this looks like this. Here I have the point 0, 0. Here I have the point d0. And here I have the point 0d. And the convex hull is all of this. I also have a lattice inside R2. And I claim that the combinatorics of a tropical curve are completely determined by a lattice subdivision of this polygon and vice versa in the following way. So given a tropical curve, let's call it gamma, and let's say it's defined by the tropical vanishing locus of P of degree d, then we can define a lattice subdivision in the following way. Of delta d, such that if I have my tropical curve here, let's call this subdivision S gamma. And I want that the vertices correspond to maximal cells of my lattice subdivision. The edges correspond to edges. And the connected components of R2 minus this tropical curve gamma correspond to vertices, such that inclusions are inverted and dual edges are orthogonal. Okay, let me explain this to you. So here you see that if I go from one side to the other, the dimension is inverted. So here the maximal cells are two-dimensional, the vertices are zero-dimensional. Here we have both one-dimensional. Here this is two-dimensional, while these are zero-dimensional. So it makes sense to ask that the inclusions are inverted. So if I have a vertex of an edge, this should the corresponding edge should better be an edge of the corresponding maximal cell of this vertex. Also, dual edges should be orthogonal. And now I claim that a tropical curve gives me a unique dual subdivision, and also that this dual subdivision gives me the combinatorics of the tropical curve. So let me give you an example. Let's d equal to 2. So let's look at the tropical curve of degree 2. So this is defined by a tropical polynomial of degree 2. And this could, for example, look like this. So now we want to subdivide this guy. So here's the 0, 0. Here's the 2, 0. Here's the 0, 2. And I drew all these other lattice points. So I now need to draw through each of these edges an orthogonal edge, and I get the dual subdivision. So these unbounded edges here correspond to these boundary edges here. So I just draw orthogonal edges to these bounded edges, and I get the following. I can again just draw orthogonal edges here, and I get my tropical curve back. So this is how this duality works. And I have introduced this for two reasons. I will need this later to give the statement of the theorem that relates a tropical count to an algebraic count, and also for the following reason. If you believe me that this is true, we get the following consequence. Yes?
So how these lattice points correspond to monomials.
Yes.
The edges we got there by equating them, monomials have the same maximum. There is regional polynomials.
Yes, yeah.
So is there an obvious correspondence within the monomials that correspond to an edge?
Yeah, so that's very easy. So here will be the monomial x to the 0, y to the 0. This corresponds to the point 0, 0. Here it's x to the 1, y to the 0. So this is 1, 0. Yeah. X squared, x, y, y, y squared. Like this. Yeah, exactly.
I see.
So this
your edge came between, you had a y and a 1 in your polynomial, and they give that edge between the two for an edge on the curve.
I didn't.
You have when you tropicalize your original function,
Yeah.
it makes all those things into linear terms.
Yeah.
And then they become equal. They have maximum.
Exactly here.
And the edges are where the two of them become maximum.
Exactly.
Right.
Yeah. Okay, so a consequence of this is what is called a balancing condition. You already see that these tropical curves, they are not completely arbitrary. They follow some rules, and here's the rule they follow. It's called the balancing condition. Namely, the sum of primitive vectors times the weight is 0. So now I have to tell you what these are. So here's an example. Assume we have a vertex of our tropical curve, something like this. And the dual picture is a quadrilateral like this. So let me also draw the lattice points in here. So this is just locally a tropical curve, and the dual picture is this guy here. So here we have weight 3. Yeah, right. I should have said that edges of weight W correspond to edges in the dual subdivision of lattice length W. So this is also a way you could define your weight. So what do I mean by lattice length? It's really the number of lattice points on your edge minus 1. So the balancing condition tells me that if I take, so these all have weight 1, and if I take the shortest integral vector in each of these directions, so these are the VI, so let's say V1, V2, V3, V4, then taking the sum of these vectors and multiply them by the weight, we get 0. So in this case, this would be 3 times 0 minus 1, going down, plus 1 times minus 1 comma 0, plus 1 times 2 comma 1, plus minus 1, 2, and this is 0, 0. So why am I telling you that? First of all, one can Mikhalkin proved that. So here, this shows it follows from this dual subdivision that tropical curves satisfy this balancing condition, but also the other way around is true. If one has a balanced graph, then this is a tropical curve. But from this, we get the following enumerative statement. Yes, please.
So first of all, why is the picture now not a triangle anymore?
This one? So this is just locally. This should sit in a big triangle. Actually not. It could also be like tropical curves. One can also define them with subdivisions of other Newton polygons. But let's assume this is just a local picture and it sits in a big triangle. And then this is a 4-valent vertex. So this should correspond to a cell with 4 edges by this dual subdivision. But yeah, thank you. This is actually, but this should be a local picture.
The other question is, what do you mean you might want to recover the curve from the subdivision?
Yeah. So this is.
You have infinitely many polynomials, finite different.
I can't recover the exact curve, but I can recover the combinatorial type by just drawing orthogonal edges again. So it doesn't tell me how long. I could stretch this edge and I can move it. So it doesn't give me the exact curve back, but it gives me somehow the isomorphism class of this tropical curve back. All right. So now. So why did I do all this? I want to claim that these tropical curves, I want to count algebraic curves, and I claim that counting tropical curves is much easier. So here's why. Let's at least count tropical lines, and I claim that given two distinct points in R2, and they should be general enough. There is exactly one tropical line through them. So why is that? First of all, this should really remind you of the classical case. If you have 2 points, in the plane, there's exactly one line through them, and this is also true in the tropical world. So that's kind of nice. So I could either have my points arranged like this, and then the only tropical line that goes through them is this one here. So the third one, we know that these have to. The only tropical line looks like this, and these 2 points give me where these 2 edges are. Then I could have this point configuration, and then the unique tropical line through them is this one here, and then there's another case like this. So that's good. This tells me that 2 points determine a tropical line. So let's do the degree d equal to. That's not allowed. That's not tropical general position. Yeah. Yeah. So one way to always get general position is to arrange your points kind of like this. This is called vertically stretched. And remember that in the plane, there's a unique conic through 5 points, and this is also true in the tropical world. So I have to draw these two, and then by the balancing condition, this one goes up here. Then I have one guy here. I have to rearrange my points. So I claim this is also true in degree 2 without a proof, but maybe the picture tells you something. Like these 2 points would give me where this edge is going. Then this edge is determined by these 2. This edge is determined by these 2, and then the last one is determined by these 2. And for degree 3, I didn't want to draw all of them, so I have it on my computer. So let's hope this works. So I want to count the number of degree D curves, tropical curves, through the correct number of points. And the correct number of points is just like in the algebraic case, 3D minus 1. And here it is. And here you can see a configuration of 3D minus 1 for D equals 3. So of 8 points So I took the same configuration. I just had them vertically stretched, going down like this. And here you can see all tropical curves through them. And there are finitely many. These are all. And you also see that I assigned some multiplicities here. Let me tell you what these multiplicities are. So the multiplicity of a tropical curve is the following. I take the product over all 3 valent vertices. I take the triangle dual to my vertex. So if I have a vertex and here of valency 3, in the dual subdivision there is a triangle, and I take the double area. So this here is the double area. And here you can see all the multiplicities, hopefully. The first one has multiplicity 2. That is because we have this one weight 2, so the triangle looks like this. So here is if you see the 2, this corresponds to this dual edge. So we have 2 triangles of area 1, so the double area is 2. And 2 times 2 is 4, so the first multiplicity is 4. All the others, the weights are all 1, and it turns out that all of these multiplicities are 1. And if you sum all of these up, you get 12. And maybe you've seen the number 12 before. 12 is actually... What?
He's never seen that.
Very good. But maybe this reminds you of something, namely 12 is the number of rational plane curves through 8 points. And we've already seen that there's exactly one line through 2 points, tropical lines through 2 points, like in the algebraic case. And also for the conic, I claimed that there was only one unique tropical conic through 5 points. And this is exactly what Mikhalkin's correspondence theorem says, namely, if there's ND, but there's N3, the 12, if I take a sum over algebraic curves and count each of them with a 1, then this actually equals ND trop, which is I take the sum over a tropical curve, but I count them with this multiplicity I just introduced, and here are the examples. So here, what do the sums go over? Sum over rational. In the first case, it's the sum over rational algebraic plane degree D curves. And in the second is, instead of algebraic, I take tropical, also degree D curves. So they are defined by the vanishing of a degree D tropical polynomial. And both are through 3D minus 1 points. In the first case in P2, and the second case in R2. Yes?
In the tropical case, you get this finite number of combinatorial types when you fix the points. But when you change where the points are, the points will land up on different places on the curves. Are the combinatorial types all the same, regardless of which points you choose, or can you get different combinatorial?
I think you get different. You can get different combinatorial types, but yeah, you can get different combinatorial types, and also the multiplicities can change. But there's still an invariant. If you move the points, you can still show that the sum is invariant. And what was that? Yeah. But you can get very different tropical curves and combinatorial types. Right, and here's the Mikhalkin's correspondence theorem, which says that, as we've seen in the first 3 examples, for D equal to 1, 2, and 3, that ND actually equals ND trop. And here you can see the computation of ND trop. It's 12, and this is actually also the algebraic count. And it's gone. Right. I don't tell you how to find all of them. There are actually algorithms to find all of these these tropical curves, and it turns out to be rather simple. So I hope I could convince you that counting tropical curves is easier than counting algebraic curves, and now I'm already more than half of my time has gone, so now I should really tell you how to do this over other fields. So let's first do this in case of the real numbers.
So, and when the curves cross and you get a crossing point, that corresponds to a double point on the algebraic?
Yes, exactly. These crossings here, these actually come from a node. And in the first picture, you don't have the cross, and the node is hidden in this double edge, in the multiplicity 2 edge. Yeah, I guess. Can I erase this? Then I can keep the picture. Okay, good. So let's do this over R. So now counting, let's actually do the actual problem we want to do. Algebraic curves over non-algebraically closed fields. And let's start with the real numbers. We've seen that n3 is 12, but I claim that there can be 8, 10, or 12 real plane curves, real rational plane curves through 8, which is 3 times 3 minus 1, real points in P2. Of course, all in general position. But Grothendieck-Witt tells you how to get a real count independent of the point configuration. Real count independent of the point configuration. So here, these numbers, 8, 10, and 12, they depend on the chosen configuration of real points. But Grothendieck tells you how to get an independent count, namely by classifying real curves into 2 types. We've already discussed that each of these tropical curves has a node, and this is also, from the degree genus formula, this is also true for degree 3 curves. They will have a real node if I have a real curve. And there are 2 types. Of real nodes, namely one split node, which looks like this. It has 2 real branches. It's locally defined by the equation x squared minus y squared is equal to 0. And the other one is, let's call it solitary node, because it only has like 1 point and then 2 complex conjugate branches. And here, the local equation is x squared plus y squared is equal to 0. And Grothendieck shows that the number of, let me just write curves, so it's degree 3 curves, rational plane, real curves, with the split node minus the number of degree 3 curves with a solitary node is always 8. So in the first case here, all of these curves have a split node. In the second case, 9 will have a split node, 1 is solitary. Here, 10 will have a split node, 2 a solitary node. And let's call this W3 for Verchonget invariant. More generally, one can define the type of a real node. Let's define it to be +1 or -1 in case the node is split, and here if it's solitary. And we can define the Verchonget sign of a real curve to be the product over all real nodes, Z of the types of Z. And just like in this case where the degree is 3, if I sum up these Verchonget signs, this will be an invariant. So this is Verchonget's theorem. So let's say let's call it WD, which is the sum over all of these Verchonget signs, where we sum up over all the real curves through this also rational plane degree D through 3D minus 1 points, real points, is invariant. So I mean independent of the choice of points. And actually, there's also a correspondence theorem for this count. So there's also a tropical count, a real tropical count, and I don't have any space. But maybe this comes later. Because now, let me first tell you how to generalize this. So what about other fields? So let's let the characteristic of K not be equal to 2. And let's also study the types of nodes defined over K. So we've seen that here the count depended on the types of nodes, and let's see how one can generalize this. So here there's also the split node, this picture. Let me write the equation as follows. I take x squared minus alpha y squared equal to 0. Let's assume this is the local equation for some alpha a square. So alpha shouldn't be 0, and it's a square. Because then this equation splits into two linear factors. And the solitary node, where I have two conjugate branches, and I take the same equation, but now alpha is not a square, so this equation doesn't split. Earlier, I called this alpha the type, so let's do this again. So I want the type of a node to be the image of alpha in units of k squared. And observe that actually for each class, so I identify two units in k if they only differ by a square, and for each class there's a different type of node. If this is a split node, I can also replace alpha by 1, so this is really just the same class, but here there could be different classes corresponding to the different classes in here. And here this type really tells you where these branches will be defined over a quadratic extension of k, And this type tells you exactly which square root you have to join, namely alpha, the square root of alpha. So I claim that this is the natural generalization of the type of a node. And this is quite good, because I know we've seen this earlier in the talk. These are exactly the generators of the Grothendieck-Witt ring. And we've also seen in the talk just now, and I think also in the morning, that this is really the natural place to do enumerative geometry. So recall that GW of K is generated by these classes of quadratic form. So this is this quadratic form ax squared. And we have a generator for each unit, 1 unit squared. So instead of remembering the class in here, I could just stick brackets around it. And that's exactly what you do. So I think Mark was the first to define this. So we can define this generalization of the Welch sign, and it would be a quadratic form to be, you take the product of all the nodes of the curve C over the types. But we actually want to record all of them, so we trace down from the residue. We take the norm from the residue field of the node to K and get an element in Grothendieck-Witt and stick brackets around it. And as a remark, this actually really generalizes what we've seen before. If I take K to be the real numbers and to stick the brackets around it, this is exactly this here. Why is that? Well, the only thing that could happen is that the nodes are defined over the complex numbers, but then the norm will give me something positive, so it doesn't contribute anything to the sign of this. And now I'm running out of time. But where do I want to go with this? It turns out that we have a result like this. Also for counting curves over an arbitrary field, almost arbitrary field, when we take this weighted count with these quadratic weights with these guys. So okay. So theorem. So I want to, there are two papers. There's one by Mark, and then there's a new preprint by Jessica, also Mark, Jake Solomon, and Kirsten Beckelgren. And let's call this NDA1, and then maybe let's also put the K into the notation, where I sum up over all curve C. Your sum is over all plane rational degree D curves C through, let's say, 3D minus 1 K points. You can also allow more general configurations of points, but let's stick to this here. This is independent of the choice of points, and then you still need to tell you what I get right here. So here I want to put this here, but not quite. I actually want to take into account all of the curves. So the ground field of the curve might be a field extension of K. So let kappa of C be the ground field of the curve, and compute this quadratic weight in here, and then trace down. This gives you an element in Grothendieck-Witt. Okay. And one reason for this is the following. One can express this nd of k, or at least this paper here shows that this is the degree of a map, namely of the evaluation map from the moduli space of genus 0, 3D-1 pointed stable curves in P2 of degree d to, here we have 3D-1 copies of P2. So this paper here shows that this evaluation map, there's a well-defined degree of this, which lives as a 1 degree usually does in Grothendieck-Witt of k. But also, now we can take a configuration of 3D-1 k points here and look at the pre-image in here, and this will be exactly the curves through this point. And then this splits up as the sum of local degrees. And it turns out that these local degrees are exactly these guys. So this is not a proof, but maybe you have an idea where this comes from now. This is really just like in topology, you can define a degree of a map between manifolds and write this as a sum of local degrees. This also works in Motivic homotopy theory. And it turns out that these local contributions are exactly these guys here. And this thing is independent of this point in here, while here you pick a point configuration. Okay, so now I have to tell you how to do this, how to compute this, and of course I want to use my tropical geometry for this. So that's the last thing I want to do, and then I'll get this picture again. Yes?
The Radboud result, you were summing over real curves.
Yes, yeah. Very good, I also get this. Yeah, so here there could also be a complex one. So if I have the trace of C over R of this well-changé thing, so in the Grothendieck-Witt ring, the generators would be in here, which is just, everything has a square root. So this is just 1, so I want to take the trace of 1. Is that okay until now? And this is 1 plus minus 1. So if I leave, so in the real case, we didn't put the brackets, and then we would get the 0. So that's like the natural generalization of this. Yeah, exactly. This also, just like Mark says, this is also something that really follows now from the following. Let's do quadratic tropical counts. So I already told you that there's also a real multiplicity for the tropical curves. And this looks as follows. There are two cases. Either this is -1 to the number of interior points in the triangle. I'll write this down in a second. In case all edges have odd weights, or 0 otherwise. So what is this int? Int is short for interior lattice points in triangles of the dual subdivision. There's actually one example I should maybe give where this is not trivial. So here's a degree 3 curve. This is also a different combinatorial type as than we saw earlier. So let's say we have this degree 3 tropical curve, then the dual subdivision looks as follows. Let me draw the lattice points here. Like this. So why am I drawing exactly this? Here, there is one interior lattice point in one of the triangles. So here, the real multiplicity is -1. Okay. Then, can I erase this? Is that okay? Now I have to tell you. Now I want to tell you what the quadratic multiplicity should be. It's the following. So let's decorate it with an A1. And this is either -1 to the same, what I called int here for interior points, in brackets, plus the product over all 3 valent vertices of the tropical curve of this double area of the dual triangle, this -1 divided by 2 times h, where h is the hyperbolic form, so that's 1 plus -1. Or it's just this guy here divided by 2 times h, and we have the same case as before. Here all edges have odd weight, and here else. So for example, here, this A1 multiplicity would be -1 in brackets. And the product of the areas of these triangles, or the double areas, is these all have area 1/2, so the double area is 1, but this one is 3, so we have 1 hyperbolic form here. And maybe this, you recognize this from earlier, this was exactly the multiplicity of gamma I had earlier when I counted tropical curves. So I can also write this as the real multiplicity plus the multiplicity of gamma -1 divided by 2 times h, or just the multiplicity of gamma divided by 2 times h in the same cases. And now the theorem, and I'm already over time, so I don't have time to say anything about this. Okay, good. Very good. Then I can finish. So this is joined with Andrés. And this one says that here we need either that the characteristic of k is bigger than the degree, or the characteristic of k is 0. And then this nd a1 of k equals nd a1 trop of k. And this is exactly what it should be. It's the sum over all the tropical curves over these A1 multiplicities, like this. Of course, I could also define WD trop as the sum over these guys. And here, of course, the sums are all the topical curves through a given configuration of points. And there's another correspondence theorem by Mikhalkin also that shows that this is actually the same. And now you already see that for the multiplicities, the signature, so when the signature just turns h into 0, you get the real multiplicity back. And the rank, so you just count the number of summands, then you get the complex multiplicity back, or just the multiplicity. So as a corollary, we get that this actually is the following. It's nd minus wd divided by 2 times h plus w times 1. So, and for these, there are combinatorial formulas to actually determine these. And now let me finish with the picture again to show you what this means for degree 3. Okay, maybe not. Ah, now it works. Okay. That was the first picture where we just had the multiplicities. Now, here I added some real multiplicities. So the first one has one edge of even weight, so the multiplicity is 0, and we get the 8. That's the one we already had earlier on the board, this sign count of real curves. And now, hopefully, this is still on the picture. I know. But here's this A1 multiplicity. The first one is just 2 hyperbolic forms. All of these have multiplicity 1, also in the A1 case. So what we get in the end is 8 times 1 plus 2h in the Grothendieck-Witt ring. But this also follows from this corollary. But maybe this illustrates how one can count these using this correspondence theorem. And here I should stop. Thank you very much. There's a couple of problems, like even if now, okay. So I forgot to say that also Mark's theorem I stated earlier, you have to exclude characteristic 2 and 3. But then Mark explained to me that once we know it for a big characteristic, since this problem you can define over z where you invert some number, he doesn't know, 2 or 3, that's enough? Okay, so one can, if this is true, this is actually true for a characteristic not equal 2 and 3, right? Because we can actually define this problem over z with 6 inverted, and then this map that maps into the Grothendieck-Witt ring of K with some bigger characteristic is injective, and then you know what it is.
So you know what it is up to things are going 2, 3, and 6.
Yeah.
And then you can check those for a lot of large primes to see that they're not close. You just see, take a prime where 2 is not a square, but 3 is, for example, and then that'll tell you 2 factors. So once you know it for all large primes, and you know the thing exists over z adjoin 1, 6, then essentially know what you have a uniform formula for all large primes. There is some formula over z.
Does the counting problem still make sense if there's 2?
Well, like you still need to find it, so it definitely doesn't make sense for F2 because there's not enough points. So you but if you have like a big enough field so that you actually have a configuration in general position, yes.
Is there a geometric interpretation of this last multiplicity?
Okay, yeah. I actually spent far too much time explaining what tropical curves are because I got excited. So I wanted to say how this actually works. There's a way to actually take an algebraic curve. So what you should think about is you generate it, and in the generation, you generate it so much that you get a tropical curve. So that's very vaguely said. So you can assign one tropical curve by a degeneration process to an algebraic curve. And then this multiplicity is really, you count all of the algebraic curves that degenerate to the same tropical curve, and you just sum up these quadratic weights for them and then call this the multiplicity. And for some magic, like the single algebraic curves that tropicalize to the same tropical curve, they don't have only ones and minus ones. But if you sum them up, only ones and minus ones are left.
From Mikhalkin's theorem, right? Like for the
the
version you proved, for instance, does this degeneration, interpretation still make sense? Like, what's the degeneration of a curve over K to?
Yeah, I mean, there's also an algebraic way to do that. So it's not Mikhalkin's proof that works here. Like, this was very analytic, but there's an algebra. It still makes sense. I don't know, yeah.
That's something like mixed characteristic.
Uh,
way is like we apply this logarithm map, produce an amoeba.
Yeah, no, but no. There's also an algebraic way to do this by using Puiseux